Hi, ladies and gentlemen. Welcome to Chapter 4. We're going to start talking about interpolation. To start, we're going to begin with polynomial interpolation, and then we're going to move into piecewise interpolation with spline functions, and then finish up with curve fitting. Hopefully, we'll be able to do some linear as well as nonlinear curve fitting. We'll see how the time works out for us. But to start, we're going to take a look here at Chapter 4. I encourage you, of course, to read the introduction and look at the definition of interpolation. That's very important. And what we're going to do is start with the easiest thing, which is linear interpolation, which is literally drawing a line through 2 points. And there are a couple of examples here which follow along with exactly what you understand the development of a line to be. And so what we have are y is equal to the slope. This is the rate of change given the 2 points. And this is x minus a point value, x naught, plus the associated y value, which is y naught. So this is the line using the point x naught, y naught for the expansion. Right below that is the same idea, except we've used the point x1 and y1. And it turns out that they're going to, of course, be the same equation. It's going to be the same line. And that's a hallmark for polynomial interpolation. We will look at later the fact that there's only one polynomial interpolant of the correct order that goes through a set of points. So this is an important, so there's a little bit of algebra here on the end of page 105, starting 106. And then we end up with this result right here, which is fundamental to what we're talking about in section 4.1. And what we have here, you can see it's rewritten down here. This is a standardized form for polynomial interpolation. We have two functions, which are L naught as a function of x and L1 as a function of x. Those are called Lagrange interpolating polynomials. And the form of the Lagrange interpolating polynomials is right here. So you just want to look through this and see how just a little bit of algebra can take the line that we have and break it apart into two sections here that are weighting the different y values. So this function, this Lagrange interpolating polynomial, is weighting the y naught value, while this one is weighting the y1 value. And that's something that we're going to see through the rest of this section. All right, so let's move on and take a look at what happens if we have more than 2 points. So in the case where we have 3 points, then we're going to fit a parabola through our data. And before we get to that, let's take a look at how we could have written the line using linear algebra. So in general, what we have is this equation here for a line. And we can substitute in the data, and it's going to give us 2 equations. So this is, of course, the hallmark of 2 equations and 2 unknowns. We know that we can solve this to find m and b, specifically the slope and the intercept. So while the line's not in the same form as what we were talking about in the textbook, it's of course the same line. What I want to do is just write this down in matrix form, however. So what we have is we have a matrix of coefficients multiplied times the unknowns, which in this case are m and b, and that's equal to some set of values. Remember, each row is an equation. So this is the first equation, which is 1 times b, and sorry, I've got that in the wrong spot. So the first equation is the first row. That's 1 times b, m times x naught, and that's equal to y naught. The second equation is here. M is multiplied by x1, b is multiplied by 1, and the value is y1. So we could use linear algebra to solve this problem, and we would find the same line that we found earlier. And what we're talking about here is having 3 equations with 3 unknowns in the case of 3 distinct points, and we can put a parabola through those. So to do that, we would set up our equations in matrix form. Let me show you. As we did previously, we're going to set this up with the unknown vector. I always recommend that's where you start when you're solving these types of problems. And what I want to do is remember every row is an equation. Now look how I've set up the coefficients in the vector, because that determines the coefficient matrix. The A naught is multiplied by 1. The A1 is multiplied by x naught. The A2 is multiplied by x naught squared, and that's equal to y naught. And you start to see the pattern here. A naught, look at the equations over here. A naught is always multiplied times 1. So this is an entire column of 1s, because remember how we do matrix vector multiplication, the A naught is multiplied times this column. So we have all the A naughts multiplied right here. And the A1 is multiplied by the x value for all of the equations. Similarly, the A2 is multiplied by the square of the x values, like this. And then, of course, they're equal to their respective y values. And so we have this very systematic way of setting up the equations. Again, 3 equations and 3 unknowns, and as long as the points are not collinear, we will be able to solve this and find unique values for A naught, A1, and A2, and we'll have one parabola that fits through those. So the following conversation on 107 says, hey, what if we just have a number like 50 points? Can't we just set this up and solve it? And the problem is we cannot. So what you'll notice is the A naughts, of course, are always multiplied by 1, and the A1s times the x values, and A2 times x squareds, etc., up until the last coefficient, which is multiplied by the x values raised to the nth power. It's easy to see how we could easily have an x value in the range of 100, and as soon as we reached a 9th or 10th order polynomial, we'd have 100 raised to the 10th power. And we'd end up with 1 times 10 to the 20th. So if this is 1 times 10 to the 20th, and this is 1, given the floating point arithmetic limitations of the computer, we're not going to be able to solve this matrix. So for theoretical purposes, this is a really nice construction. But when it comes to computation, it's almost useless. The setup here is called a Vandermonde matrix, and it is ill-conditioned, as we just discussed. All right, so what we're going to do instead is use this format and Lagrange interpolating polynomials. And these are examples. I'm going to let you look through the examples, and I'm going to let you look at this result here, which is critically important. The Lagrange interpolating polynomials are set up so that at their specific point, they're equal to 1, and at all the other points, they're equal to 0, all the nodes. And by nodes, we mean the x values. So when I feed in the x value for that Lagrange interpolating polynomial, it evaluates to 1. When I feed in any other node along the course, it evaluates to 0. And the result is, this is a basis. We have a basis, and what we do is we construct the polynomial for interpolating as a linear combination of the bases. And that's what we see here in this example. This is a demonstration of the linear combination. So the graphic on page 109 shows you how these Lagrange interpolating polynomials are built. So in the case where we have the data with nodes at -1, 1, and 4, the 0th Lagrange polynomial equals 1 at the first node, which is -1, and equals 0 at the other nodes. L1 is equal to 0 at x0. It's equal to 1 at x1, which is the second node, and then at x2, it's back to equaling 0. So this allows us to very easily construct what we need for interpolation. In general, the way we build these Lagrange polynomials is using this product. Let me break this down for you and show you just how easy this is. I'm going to start with an example where we have 3 points. So we're looking for a parabola. So we're going to create 3 Lagrange interpolating polynomials. The way this works is, I have yet to determine a j value. So let me write down specifically, if I want L0 of x, what I'm going to do is I'm going to basically put in x0 into all of the values in the denominator. So this is going to be equal to, so here's my denominator. But what you'll notice is, of course, we have a serious problem, right? We can't have this thing here. So we're going to need to remove that. And what we do is we come back up here to the original and we remove this entire piece of the Lagrange interpolating polynomial constructor, if you will. And so we're going to remove this thing. We're just going to take it out. It doesn't divide away. We just remove it. And then what we're going to do is we're going to keep the remainder of the numerator, x minus x1 and x minus x2. And so through this really simple formulation, we end up with what we want. L naught evaluated at x naught is equal to, and you can see, if I put x naught in here and x naught in here, I'm going to end up with 1. And that's what we want from our interpolating polynomial. That's 1. If I evaluate this at x1, well, then this term becomes 0. And so this is equal to 0. Similarly, if I evaluate this Lagrange interpolating polynomial at x2, this term becomes 0. So you can see how I've just constructed a polynomial that does exactly what I want it to do. By removing this term here, I'm able to create a polynomial that evaluates to 1 at x naught and 0 at all the other nodes. And then using this generalized constructor here, I can easily create L1 and L2. I'll show you. So you can see here for L1, I've done exactly the same thing, except this time, since it's associated with the node at x1, that's what this 1 here means, then I've removed that chunk and then I've subtracted x1, or put x1 into the values in the denominator. So I have x1 minus x naught and x1 minus x2. And then L2 is the same. So you can see I have my L2 Lagrange interpolating polynomial, which was constructed by removing this portion here from the generator and using the other two pieces, using this part, and in the denominator substituting in x2. So that's all it is, and that's all this thing here says. This product is giving me exactly what we just discussed. So here's another example, 4.1.2. I recommend that you take a look at it. And it has a nice graphic here showing the Lagrange interpolating polynomials. Now what you notice is, for example, L naught on the first node, which is at 0, is equal to 1. At all the other nodes, it's equal to 0. And then similarly, as we go down, L4 is equal to 0 at all the nodes until the last node where it's equal to 1. And so this just allows us to easily construct interpolating polynomials when we have a set of data. So the problems are here, largely about looking at Lagrange interpolating polynomials along with some compare and contrast with Taylor polynomials. As before, and I apologize, here's an example where it's not referencing problem 4, it's referencing problem 60 because the numbers of the equations have not updated correctly in the text. So this is a comparison of the Taylor polynomial versus our interpolating polynomial. And we'll discuss why that's important later on. All right. That's all I have for this lesson, and I look forward to seeing you in class.